Okay, welcome everyone. So today it's my pleasure to welcome Fiedler, who will be talking about producing kernel-based spaces in the field limit. Yeah, thank you.
Okay, so thank you very much for the invitation. Thank you also very much for organizing this very interesting seminar series. And a warm welcome from Aachen, from very warm Aachen, to be honest. And it's my great pleasure today to talk about reproducing kernel Hilbert spaces in the mean field limit. So this is joint work with Michael Perti, Michael Rom, Chiara Sigala, and Sebastian Timbe. We are all from RKHS Aachen University. And the stuff we will see today can be found in two publications. One is out in kinetic and related models. The other one is currently under review. And hopefully, the reviews come back very soon, and we can then upload the preprint. So here's the agenda for today's talk. We'll start with a brief introduction and motivation. How we got to this topic in the first place, where we came from. Then we will talk about what exactly we mean by the mean field limit of functions and kernels. Then we will apply all of this to reproducing kernel Hilbert spaces. Particularly, we will look at certain relations between different RKHSs which appear in this context. And then more like an outlook, we will then close by discussing what all of this means for kernel-based statistical learning theory. Okay, so let's get started. Brief introduction and motivation of all of this. So originally we were interested in so-called interacting particle systems or multi-agent systems. So these are dynamic systems where you have many entities which interact with each other. A very classic example from physics are, for example, gas dynamics. In this case, as you probably know from statistical mechanics, first principles modeling has been applied in a very successful manner. However, recently, this class of systems has been applied to other domains, to many complex modern applications. For example, the dynamics of pedestrians, or more general vehicular traffic dynamics, but also animal motion and even social dynamics or opinion dynamics. Now, in these domains, these more complex domains, it's not surprising that first principles modeling is often not really feasible anymore. However, because nowadays we live in an abundance of data, we can as well use machine learning methods to learn about these systems instead of modeling them from first principles. Now, most works in this realm consider the question of how to learn the interaction rules from trajectory data. This has been, I would say, a flourishing subfield since approximately 2017, when the first mathematically rigorous works came out. However, we are interested in a slightly different question, namely, what if we want to learn functionals on the state space from snapshot data? So let us make the things a bit more precise. So suppose we have a given state space of the individual agents denoted by X. So usually this is RD, or maybe even just the unit interval or unit hypercube. And consider a multi-agent system or a particle system with M agents or particles, depending on the application. Now, the state space of this whole multi-agent system then is simply the M-fold Cartesian product of the state space of the agent, so Xm. Now, the evolution of agents from a given initial state, assuming deterministic dynamics for simplicity, is then nothing else than a trajectory in the state space. And this, for example, can be modeled using an ODE. Now, we are interested in functionals on the state space of this multi-agent systems, which formally is nothing else than a scalar function on the state space, and it can be interpreted as a certain feature of the multi-agent system in a given state. For example, such a function could be the mean or the variance of the states. I mean, obviously, these are almost trivial examples because if you know the state, I mean, you can simply calculate it because they are defined by a closed form formula. However, as I said, lately, these type of systems have been applied in more complex modern domains. For example, suppose you want to do social dynamics modeling, opinion modeling, which has been a rather active topic for the last, let's say, 10 years. And then you can ask questions like, okay, what is the, let's say, satisfaction of a given society modeled with this type of system, or even the aggression potential, given, for example, if the state space is the form of abstract opinion space. I mean, these questions are considered in particular by physicists and applied mathematicians in this domain. I mean, obviously, it's very, very difficult modeling such a functional. So, I mean, once again, the basic idea is, can we learn this from data? So suppose we can collect potentially noisy measurements of our functional at different state snapshots. So formally, suppose we have n snapshots of the state of our system, and we then evaluate the functional on these states, maybe with some measurement noise. Now, one way to do this is, for example, if we have indeed a multi-agent system, which is a dynamic system, then we simply let the system evolve or observe an evolving system and take snapshots at certain sampling times, T1 to Tn. And this leads then to state snapshots, which we, let's say, assume for simplicity that they can be measured exactly, and the potentially noisy measurements of the functional of interest. Now, this is then nothing else than a data set of input and output pairs. And learning this functional is then nothing else than a regression problem. So it can be solved basically by standard supervised learning methods. Now, if you use a kernel method, then we fix a kernel. And usually then the function is approximated by an approximant of the following form, which is essentially just a weighted sum of the partially evaluated kernel at the inputs from the dataset. And I mean, this form usually arises from a representer theorem. Now, observe that in this case, we need a kernel on the space XM, because this is then the input space of our supervised learning program. Now, in many applications of interactive particle systems, of multi-agent systems, the number of particles or agents can be very large. I mean, for example, if you do modeling of animal motions, I mean, if you think of a flock of birds or a fish school, you have thousands of animals. If you are modeling, for example, colonies of microorganisms, you might have millions of entities, agents. Or if you do, let's say, classic statistical mechanics, for example, gas dynamics, you have an enormous number of molecules to deal with. And I mean, obviously, then working on the microscopic level, working with each particle individually, is then intractable, in particular when it comes to numerics. So a classic idea in statistical physics is, instead of modeling each particle individually, you only look at the distribution of particles or their state space and how it evolves. So formally, the state space of the multi-agent system or in a particle system is then the set of probability distributions over the state space of an individual agent. And the evolution of our agents from a given initial distribution or measure over the state space is then a trajectory in the space of probability distributions over this state space. And this can be modeled, for example, using a PDE. Now, if we are again interested in the functional of the state of our multi-agent system, then this functional is simply a function on probability measures over the state space X. And the question arises, okay, if you still want to do learning, how does the learning problem now look like? Well, I mean, completely analogously. So suppose we have state measurements, state snapshots, which in this case actually correspond to a finite number of measures with the functional evaluated at these states, potentially again with noise. And this can also in a completely analogously manner done as in the case of finitely or with discrete agents. We, for example, evolve the system which means you have an evolving distribution. And then at certain sampling times, you basically take a snapshot leading to one fixed distribution. Now, once again, our function, which is now a function on probability distributions, can still be approximated from data. And it's still a supervised learning program. Now, if we want to use, again, kernel methods, we have to fix a kernel. And then once again, usually we work with approximates of the form given on the slide. But now, the kernel is actually a kernel on the set of probability distributions. I mean, there are kernels out there for this. I mean, starting back from, I think, 2005, and then extended and popularized by Steinberg and Christmann, 2010, for example. So there's basically a decent collection of appropriate kernels available for this task. However, in kinetic theory, so this is the corresponding sub-branch of statistical mechanics, or statistical physics, a model on the mesoscopic level as handling the distributions of agents is usually derived from a model on the microscopic level. So microscopic here means that you model each agent individually. And one way to actually derive this is using something called a mean field limit, which is a procedure if you increase the number of particles to infinity. And this is a procedure which allows you to then derive an appropriate model on the mesoscopic level. Or put in different words, if we let m, the number of agents, go to infinity in this mean field setup, then the microscopic model approaches or converges to the mesoscopic model. I mean, in practice, what you usually have is, let's say you describe the microscopic dynamics using an ODE system, let m go to infinity, and then you either formally or rigorously, you then get a PDE, usually of last of type. So the question is now, okay, if we do this for the underlying interacting particle system, what does this mean for the learning problems? And in particular, if we want to use kernel-based learning methods, what does this mean for the kernel? Or in other words, what's the mean field limit of the corresponding kernel? And this is the question we want to tackle. So let's make precise what we mean by a mean field limit of a function or kernel. So in order to do this, let us fix some notation and the setting. So we work with a compact metric space and the Borel probability measures over this compact space. And as is well known, the weak convergence, also called narrow convergence of these probability distributions, can be metrized by the Kantorovich-Monch metric, which is called here. And it's also very well known that if you use this metrization, then you get, again, a compact space of probability distributions. Now, if you have a finite number of values, points from the space X, you can form the corresponding empirical measure, which is obviously then also a probability measure. It's also very well known that these empirical measures are dense in this metrized space of probability distributions. And finally, we will also need quite a bit of permutations. So we use calligraphic SM for the permutations of the numbers 1 to m. Okay, so let us motivate the mean field limit of a sequence of functions by giving some intuition. So suppose we have a collection of functions fm, where m is the number of inputs from X. And our goal is we would like to define an appropriate notion of limit of the sequence of functions. Now, here's some intuition. So fix one Borel probability measure. Then we can find a sequence of empirical measures with an increasing number of atoms going to infinity, so that these empirical measures converge to this fixed measure. Now, if the function fm is permutation invariant, then it actually defines a function on the space of empirical measures with exactly m atoms. You simply extract the atoms out of the empirical measure, you put them into a tuple, choosing any order, and then putting this tuple into the function fm. And because the function fm is permutation invariant, so shuffling around the inputs does not change the value, this is then a well-defined procedure, and you get actually a function on the empirical measures. with exactly m atoms. Now, if we let the number of atoms go to infinity, we can actually approximate any Borel probability measure by an empirical measure. And for any empirical measure, because we have Fm with any m, we can then calculate some, let's say, feature. What this suggests is that the limit, the sequence of functions, should then be some function on the probability distributions of x. And the Fms can then be interpreted as increasingly finer discrete approximations via the empirical measures of this function f. So to a certain extent, we motivate the limit from the other way around. And if we actually then formalize this, we get to this definition. So suppose we have this sequence of functions fm. Suppose we have a function on the probability distributions. Then we say that this function is the mean field limit of the sequence of functions if this condition holds true. And essentially, this condition you see on the slide is nothing else than the intuition we just gave, plus some uniformity condition. Because the idea is it has to work for any measure we want to evaluate f on. So yeah, we simply use a sub to make things uniform. And we then also say that the Fm converge in mean field to this function. Now, apparently, this particular notion definition has been introduced by Pierre Lyons in the context of mean field games, but by now it's a very established notion in the context of analytic theory. In particular, it's used quite a bit in mean field optimal control. And note, I mean, the mean field limit does not necessarily need to be unique, but actually this won't cause problems in the developments outlined here at all. Okay, so how do we get such a mean field limit? Does it exist? There's, in fact, a very well-known existence theorem, also due to Pierre Lyons and popularized by Kadari in his notes. So here's this result. So as outlined in the introduction, we should require permutation invariance of our functions. Otherwise, things do not really make sense. We should also have uniform boundedness of our sequence of functions. And finally, we need uniform Lipschitz continuity of the sequence of functions in this particular form. And then it turns out that then there exists a limit function, which is also Lipschitz continuous, and a subsequence of our functions which converge in mean field to this limit function. Okay, so these are functions. Can we generalize this to kernels? And in order to do so, let us quickly recall some basics of kernels and RKHSs, also to fix notation. So if we have an arbitrary non-empty set and a Hilbert space of functions over the set, then we need the following definitions. So a bivariate function over the set is usually called a kernel, at least in machine learning. If there exists a Hilbert space, often called a feature space, and a map from the set into this Hilbert space, often called a feature map, such that this relation given here holds true. So the idea is you take any 2 points from the set, you map it using phi into the Hilbert space, then you take the inner product, and what you get is the same you would get if you simply apply the function k, the kernel, to those 2 inputs. So that's the intuition behind it. Now, a Hilbert space of functions is called a reproducing kernel Hilbert space if all the evaluation functionals are continuous. A bivariate function is called a reproducing kernel for such a Hilbert space of functions if, on the one hand, every partial evaluation of the kernel of this function k leads to a valid function in this Hilbert space of functions, and if we can express the function evaluation in this Hilbert space of functions by inner product, by the inner product in this Hilbert space. And this is also the explanation for reproducing kernel, because it reproduces the value of a function f. And finally, a bivariate function is called positive semi-definite if the Gram matrix which arises from any finite number of arbitrary inputs is always positive semi-definite, so in particular symmetric. And now terminology is not unique here. We really need positive semi-definiteness. I mean, the terminology is unfortunately not uniform. Now, suppose we are in the setting, then we have the following relations. A Hilbert space of function is an RKHS if and only if it has a reproducing kernel, which is conveniently then even unique. And if we have a reproducing kernel or Hilbert space of functions, then it is actually a kernel And we can use the RKHS, the reducing kernel Hilbert space, as a feature space. And we even have a very simple feature map, namely the map which takes an input and simply partially evaluates the kernel on it. This is often called canonical feature map and denoted by phi k. Now, a bivariate function k is a kernel if and only if it's positive semi-definite. And finally, if we have a kernel, then it actually has a unique RKHS, denoted by hk, for which it is the reproducing kernel. And one last fact we need. So the space of weighted sums of partially evaluated kernel, finite weighted sums of partially evaluated kernels, forms a vector space, often called hk pre, which is a subset of the RKHS. And it's very well known that this subspace extends in the RKHS. And given two functions from this pre-RKHS, we can actually explicitly evaluate the RKHS inner product in this form. Okay, with those preliminaries and notations out of the way, let us generalize the mean field limit to kernels. So the definition of a mean field limit can be, or mean field limit convergence can be actually directly generalized. So suppose we have a sequence of bivariate functions with an increasing number of arguments, so in each block, and a function on pairs of probability distributions, then we say that this latter function is the mean field limit of the former, if essentially the same condition as for functions holds true. Only difference is in the sub, we evaluate over two arguments, not surprising. And we then also say that in this case, kappa m converge in mean field limit to this limit function kappa. Now, what about existence? In fact, we can directly also generalize the existence result. So we once again need symmetry. It's enough to have this permutation invariance in the first argument. We also need uniform boundedness. And again, we need also uniform Lipschitz continuity. Now in this form, obviously involving both arguments. And under these conditions, there then exists once again a limit function. This is then a function on probability distributions or pairs of probability distributions. And it's also Lipschitz continuous, obviously then also bounded. And we have a subsequence of our kernels which converge this limit function. And very importantly, this limit function is again a kernel, and we call it the mean field limit kernel. Now, some remarks are now in order. The existence proof for bivariate functions, so that there exists such a mean field limit, is basically a direct generalization of the case of univariate functions due to Nyons and then popularized by Cadalé. So it's basically just an exercise understanding the proof and generalizing it. And here's a quick sketch of how it works. So first you extend each kernel to a function or pairs of probability distributions using the classical McChain construction. Then you show that the resulting sequence is actually equicontinuous and uniformly bounded. And under the compactness assumption we work with, we can then use simply Arzelà-Ascoli, and then we get the result. And this also explains why we only have a subsequence. Now, to show that the corresponding limit function is actually a kernel, we use the positive semi-definiteness of kernels. So that's also not a big deal to do. Important, using this approach, we cannot ensure positive definiteness of the limit kernel. However, for the following developments, this also does not play a role. It's not a problem, and it would be interesting investigating conditions under which this holds true. Now, for the remainder of the talk, we fix now a sequence of kernels, which fulfill these conditions. We also fix one corresponding mean field limit kernel, and then we also re-index the subsequence to save notation again by km. And finally, also for brevity, we call the RKHS of the kernels km simply hm. Okay, so it's time for examples. The first class of examples is given by a very classical construction called Hilbert kernels. So we fix a Banach space and a kernel on this Banach space, and then a family of functions phi for an xm to y. Now, there's a classical construction called Hilbert kernels. The idea is you take two inputs, you apply a function it, in this case, the function phi m, and then you plug it into the, let's say, base kernel K0. And it's very well known that the resulting object, which is often called the pull pack of the base kernel K0 along the function phi m, is a kernel, in this case, a kernel on XM. So we get a whole family of kernels. And I mean, an obvious idea is then, can we find appropriate conditions on K0 and the functions phi m so that the resulting sequence also actually fulfills the existence conditions for the mean field limit kernel. And I mean, it turns out it's basically, yeah, the conditions are almost obvious. The base kernel K0 needs to be bounded and continuous, and all of the phi m's need to be permutation invariant and uniformly Lipschitz continuous. And then the sequence fulfills the existence conditions. Now, here's a second class of example. So it starts from the following observation. So recall in our existence result, we wanted permutation invariance in the first argument. But we can use the symmetry of kernels to show that it's actually also permutation invariant in the second input, or more precisely, blocks of inputs. In other words, it's permutation invariant in both inputs. So actually, we can define as well a kernel of subsets for input set X having exactly K elements. So we simply take two of those sets. We then put them into two tuples, an arbitrary ordering, and then we put it into the kernel. And because of the permutation invariance, this procedure is well defined. So in other words, the kernels we are interested in are similar to set kernels. But note, set kernels can also handle cases where you have sets with different number of inputs evaluated on the kernel. But again, it seems to be similar to set kernels. So if we can basically use then a set kernel, this would then provide us with essentially another example or a potential example of such a kernel suitable for the mean field limit. And in fact, there's a very classic construction called double sum kernels, which actually can be used here. So the idea is as following. We fix a kernel, also called base kernel. And then for each m, we then simply evaluate this kernel over all pairs with inputs from the two input tuples. We sum over them, and then we normalize. And it's very well known that the resulting object is in fact a kernel, and that it's permutation invariant as we wanted. And conveniently, if the base kernel is bounded, then so is the resulting double sum kernel. What about the uniform continuity we needed? I mean, things are a bit more complicated here. So those two facts we just saw, that's well known. Nothing new. Used, for example, in Bayesian optimization over sets. Uniform continuity is a little bit more tricky. So same situation, but now we look at the kernel metric of our base kernel K. So which is nothing else than, so you take two inputs, you go to the RKHS using the canonical feature map, and then you look at the distance in the RKHS, and this is called kernel metric. And if now X, forgetting dx, if X metrized by this kernel metric is separable, then it turns out that the double sum kernels are uniformly Lipschitz continuous with respect to the converge metric, Rubinstein metric, but this time based on this kernel metric, not the X anymore. Now, for the proof, standard arguments are used, but we haven't found this exact result. But yeah, I wouldn't be surprised if it's already out there because the arguments used for the proof are really standard. And we can actually then plug everything together, and then we get the following result. So suppose we have a base kernel on the set X, and we construct the double sum kernels, and we now assume that if we metrize X, so we're forgetting dx, if we metrize X by the kernel metric, we assume that we get a compact metric space, which is not too demanding, and that our base kernel is uniformly bounded. Then it turns out that the resulting sequence of double sum kernels actually fulfills the mean field existence results. However, with dx, our original metric, replaced by the kernel metric. Okay, and before we now leave this example, there's a very curious connection to kernel mean embeddings. And so we should maybe briefly recall the basics of kernel mean embeddings. So if you have a measurable space and a kernel on this measurable space which is measurable and bounded, then for each probability distribution on the space, we can then define the following object, which is essentially just the mu integral of the canonical feature map of the kernel kappa, which is then obviously a Hilbert space valued integral. So this is in the sense of Wagner. It turns out it's well defined. And the resulting object is then called the kernel mean embedding, or KME, of this probability distribution in this RKHS. Now, here's the reason for the name. All RKHS functions are in this situation measurable. And if we look at the inner product of an arbitrary RKHS function with the KME, then we can use definition of KME, then linearity and continuity of the scalar product, and its interchangeability with the Wagner integral, reproducing property. And yeah, then we see that we get actually the mean of F with respect to the distribution mu. And this explains why this is called kernel mean embedding. Okay, so here's now the connection. So first, just let's have a look at double sum kernels. So if we have our double sum kernel, let's say Km, and then we evaluate it at two inputs. I mean, if we use the definition, then we can use the reproducing property of K0. And then we can use the linearity of the scalar product. And then we see we actually have a kernel mean embedding with respect to an empirical measure. So in other words, H0, the RKHS of the base kernel, is a feature space, and the map which takes an input, turns it into the empirical measure, and then does the KME is a feature map for the double sum kernel. Now, if we define the tuple consisting all of the same components and call it EMX, then this can be interpreted as a representation of the Dirac centered at this X, because if we then look at the empirical measure of it, it is exactly that Dirac centered at X. And we can now use this. So if we apply, or if we run this map psi, which we just defined, this feature map, and then apply the resulting RKHS function to this EMX bar, then we actually evaluate the kernel mean embedding at this X bar. So in other words, we have the following commutative diagram. So given this tuple X, we can either directly use the canonical feature map of the double sum kernel and end up in the corresponding HM of the double sum kernel, which we can then evaluate at this EMX, which is a tuple, or we can first turn it into an empirical measure and run the KME. Then we get in the RKHS H0. And if we evaluate this then at this same X bar, then we get to the same value. Now, things are interested in if we now look at the mean field limit. So assume now that we have a mean field limit, and let us fix one probability distribution and a sequence of empirical measures with an increasing number of atoms converging to it. Now, it turns out for each fixed M, we have two embeddings of a given tuple XM. So we can so we can look at the empirical measure and then use the KME, ending up in H0. Or we can extract the atoms, looking at the tuple, and then use the canonical feature map of the double sum kernel HM. And they end up in the double sum kernel RKHS HM. Now, assume additionally that the convergence in KME matrices weak convergence of probability distributions, and they are reasonable mild assumption under which is the case. Then this implies that the resulting KMEs of the empirical measures converge in H0 in the RKHS to the KME of this fixed measure. But on the other hand, up to a subsequence, we also get convergence of the direct embeddings into the double sum RKHSs HM to the embedding of phi m. Or in other words, we get two commutative diagrams. So basically going to the right corresponds to using KMEs, and going to the left corresponds to using canonical feature maps. And then going down and up, going vertically corresponds to infinite limits of infinitely many inputs. So basically mean field limit, which then translates actually under these conditions to convergence in the RKHS H0. It would be obviously also interesting whether we can go from the lower left corner to the upper right corner and the other way around. But this does not seem to be straightforward. But at least we have those two commutative diagrams. Okay, after having seen two example classes, it's now time to have a closer look at the RKHSs and how they behave under the mean field limit. So first, some intuition. Every function from an RKHS is built from the corresponding kernel intuitively. Now, the mean field limit kernel in our case arises as a, in a certain sense, uniform limit, strong uniform limit of the individual kernels Km. So intuitively, because every function in RKHS is built from the kernel, also every function from the corresponding mean field limit kernel RKHS should arise as a mean field limit of functions from the RKHSs HM. And this is indeed the case. So for every function from HK, so the RKHS of the mean field limit kernel, we can find functions FMs so that the sequence of functions FM converge in mean field to this fixed function. Here's a quick proof sketch illustrating the idea. So let us fix any RKHS function f from HK and epsilon. Now note that the mean field limit kernel is also bounded, say by CK tilde. Then in a first step, we find a function from the pre-RKHS corresponding to the mean field limit kernel, which is in RKHS norm very close to our target function f. And then by a classic calculation and boundedness of our mean field limit kernel, this is then also uniformly pointwise close to the target function. Next, if we choose an integer m large enough, we can then find empirical measures represented by tuples, so that if we replace the mu n's in the representation of the pre-RKHS function by the empirical measures, we are still uniformly close to the target function, or more precisely to the approximation of the target function in the pre-RKHS. I mean, this simply follows from the density of empirical measures and also the continuity of our mean field kernel. And then finally, we can maybe make m even larger, so that if we then replace the mean field limit kernel by the kernel Km and basically cut out the heads, so the empirical measures, and directly work with the tuples, then we are still very close. So we do not change that much. Now, and if we combine all these three steps, then it shows that we can find a subsequence of RKHS functions which converges in mean field to the target function. And finally, if you look closely at the construction, it turns out we can actually fill up the gaps so that you get actually a full sequence FM converging in mean field to our target function F. Now here's a complementary situation. So suppose we have a sequence of RKHS functions which is uniformly norm-bounded in RKHS norm. Now all FMs are symmetric. This is inherited by the kernel, and this is also a classic result on invariance induced by kernels. And also inherited from the kernel and the uniform norm-boundedness, the sequence of functions Fn is uniformly bounded and also uniformly Lipschitz continuous. In other words, it fulfills the existence result of Lyon's respectively Cadelet. So there exists a continuous function on probability distributions and a subsequence that converges in mean field to it. However, intuitively, a uniformly bounded RKHS norm here means that all the FMs have a uniformly bounded complexity, quote unquote, as measured by the kernel. Now, because K is the limit, the strong pointwise or uniform limit of the KMs, this F should then also be in the RKHS, because their complexity, while going to the limit, does not explode, intuitively speaking, due to the uniform norm bound. And it turns out this is indeed the case. So if you have a sequence of RKHS functions from the HMs and going to infinity, which is uniformly norm-bounded, then there exists a subsequence and a function from HK, so that we have mean field convergence of the subsequence, and the functions of this limit function is in the RKHS, obviously, and it even has the same norm bound. Now, concerning the proof, I mean, existence of the mean field limit, I mean, yeah, we just explained it. The FMs inherit the corresponding properties from the kernels, plus the uniform norm-boundedness assumption. Now that the mean field limit is actually in the RKHS is much more difficult. And the idea is to use a variational characterization of RKHS membership and RKHS norm, which is due to Mark Attea. And the idea is we apply this, this characterization, this variational characterization to all of the members of the subsequence. And then we can use the mean field convergence to actually construct kind of a certificate for this function f. So also this using this variational characterization, which then basically shows that, okay, yeah, f is in fact in the RKHS, and in fact it has the same, the same RKHS norm bound. Okay, and so to sum up, we can actually summarize this as a commutative diagram. So we have a sequence of kernels Km, which converge if we let the number of inputs go to infinity, in mean field to a mean field limit kernel K. Every Km, every kernel has a unique reproducing kernel Hilbert space HM, and K as a kernel obviously also has a reproducing kernel Hilbert space HK. And what we just saw is that every function, every RKHS function in HK arises as a mean field limit of functions from the HMs. And on the other hand, every uniformly norm-bounded sequence of functions from the HMs has a mean field limit up to subsequence, which is in HK and actually has the same norm bound. So intuitively, the RKHS actually can be interpreted as the mean field limit of the RKHS's HM. Okay, I mean, this is a theoretically pleasing result, but what does it now mean for machine learning? So we work in the classic statistical learning theory set. So let's quickly recap it. So we have some input set. So we have sigma algebra. Output set will be a subset of the real numbers, and also associated with the corresponding Borel sigma algebra. Then we have a loss function. This is just a measurable function. And the idea is if you have an input x, which can be interpreted as a question, if you have an output y, which can be interpreted as the supposedly correct answer, and if you give your answer t, then the cost of your answer, whether right or wrong, is then L of x, y, t. That's the intention behind it. If you then have a probability distribution on the input-output pair, a set of pair of input-output spaces, and a measurable function of inputs, then you can also define the risk, which intuitively is nothing else than f is basically an algorithm, giving for a question x an answer f of x, and then the risk is nothing else than the expected cost if you then deploy this algorithm to answer questions from x in answers in y. And if H is actually a normed vector space of measurable functions and f is from the space of a polar hypothesis space, then we can also define the corresponding regularized risk and minimal regularized risk, which is basically just the risk plus a regularization term penalizing complexity as measured by the norm. And I mean, the minimal regularized risk, well, is just the minimal risk achievable over the hypothesis space. We have an analogous setup then also for a data set, which is nothing else than a tuple of input-output pairs. I mean, then the corresponding empirical risk is basically just the average of a given function evaluated over this data set. And with loss measured by our loss function L. I mean, this notation is obviously also consistent because, I mean, we can interpret every data set also as a corresponding empirical distribution. And finally, we then have the corresponding notion of an regularized empirical risk and regularized minimal empirical risk. Okay, so what does it now? What does it now for the mean field limit? So what we have is a family of learning problems where the number of input variables is increasing. So the input sets are then nothing else than XMs. Output set is fixed, say compact. The hypothesis spaces will obviously be then the corresponding RKHSs HM for kernels KM. And then data sets are always of the same form, where the inputs are then also tuples of increasing length. And loss functions have then the corresponding form. And our goal is then to define what does it mean if there's a mean field limit of these learning problems or learning setups. Now, first, the data sets. It turns out we can straightforwardly generalize the notion of mean field convergence to fixed data sets. So a sequence of data sets has, of the same size, has a mean field limit if all the inputs converge in mean field limit. So in this case, it's just convergence in as probability distributions, and if also all the outputs converge. And then we say that the corresponding data set with inputs as probability distributions is then the mean field limit of this data set. What about the loss functions? it turns out we can derive a similar existence result. So if our loss functions are permutation invariant in the inputs, not surprising, uniformly bounded, we actually can be a bit more relaxed here. So actually in T, we can also have an increasing term. And finally, if we have a uniform Lipschitz continuity, then it turns out we can find once again a subsequence and a Lipschitz continuous function and Lipschitz continuous functions, now with measures as the first input set, so that for all compact K, we essentially have again mean field limit convergence. Only difference is that here we basically require this for all compact K, which is, and then this obviously this K, this compactum is outside of the soup. Now, we then say again, it's a mean field limit using the previous notation. And for simplicity, now let's fix such a subsequence of loss functions and also re-index the subsequence once again. And it conveniently also turns out that properties of the loss functions get inherited by the mean field loss functions. For example, convexity, which means that the loss functions are pointwise convex in the third argument. If this is the case for all the loss functions Lm, then this is also the case for the mean field limit cost functions L. Okay, in order to not go completely over time, we won't now present all the corresponding details in the setting in full glory, but only give an overview of what we have so far and where we want to go. So first of all, as I already mentioned, when using kernel-based methods in machine learning, you need usually the representer theorem to effectively work with kernel methods. And it turns out there is then a corresponding mean field version of a representer theorem, or various representer theorems to be more precise. Then it turns out we can actually completely put the standard statistical learning theory setup in a mean field limit setting, not only on an empirical level, using so working with data sets, but even with distributions. It's unclear whether the notion we developed is the right one so far. We are still looking into this, but what we have is a natural notion, and it seems to work. So basically, you get all the theoretical results you want from it. We also then have a look at support vector machines using these kernels and the corresponding mean field limit kernel. And it turns out that we get very nicely convergence of both empirical and infinite sample, also called population level solutions of support vector machines, and also their risks and regularized risks in mean field. And we even get convergence of minimal risks here, so without regularization, albeit under a technical assumption. So this is what we then have at the moment when we apply this mean field setup, this mean field results to the statistical learning theory setup, in particular with the example of support vector machines. Okay, so let's conclude here. Maybe let us give a brief summary of what we have. So we defined the mean field limit of kernels, and we also provided an existence result thereof. And we presented two fairly large classes. So one is the classic pullback construction applied to our setting, and the double sum kernels, which also have a curious connection to the kernel mean embedding. Then we also investigated the connection between the RKHSs with finite inputs or finite input sets and the mean field limit RKHS. And we also provided then a corresponding mean field limit or setup of the standard statistical learning theory setup. Now, why is this relevant? We think for two reasons. One, obviously, if you do machine learning with data with many symmetric inputs, increasing number of many symmetric inputs, this is exactly the situation we are dealing with here. And if you want to use, as we outlined in the introduction, in the motivation, if you want to use kernel-based methods, you basically end up exactly with this notion of kernels. And if you consider a large number of inputs, you end up exactly in this mean field limit setup. The other aspect is actually, it appears to be that this is a new mean field limit notion, setup, theory in machine learning theory. Because, I mean, obviously, there are other mean field limits already out there. for example, used to investigate the learning dynamics of deep neural networks. I mean, starting with Montanari and colleagues. And you can also interpret certain infinite width limits, for example, also in the mean field setup. But it appears that this seems to be a different notion to those already established settings, which seems to be kind of complementary. Okay, and finally, there are obviously open questions and also work in progress. So I only want to highlight two of those. One is the numerical implementation or approximation of the mean field limit of a kernel, which we are currently investigating in concrete instances. And the other, which I'm particularly interested in, is what happens with learning guarantees. So, for example, if you have learning rates for each m, can you get learning rates in the mean field limit? Because essentially what we have are only convergence results, which can be kind of interpreted as a form of consistency results. But what about things like learning rates? So these are, I would say, two interesting open problems we are facing at the moment, or which are work in progress. And with this, thank you very much for your attention, and I'm very happy for any questions and comments. Thank you so much.
Yeah, thank you very much. Thank you. Any questions?